little review of what we did last week, because last week's workshop and this week's workshops go hand in hand. Okay, these are the topics that I'm going to start. Okay, so let me begin the slideshow. So these are the topics that I'm going to cover: writing logarithmic equations into exponential equations, writing exponential equations into logarithmic equations, solving exponential equations by using the same base rule, solving exponential equations with different bases, and lastly, solving logarithmic equations by using logarithm properties. Okay, now writing exponential equations into logarithmic equations and vice versa. This part I covered last week. Okay, but like I said, they go hand in hand. Last week's workshop was today's workshop. Definition of logarithms to the base a. So y equals to log of base ax means a to the y equals x. So this is in logarithmic form on the left side, and on the right side, this is exponential form. Okay, example number 1, write each logarithmic equation into an exponential equation. Right, so here we have to know what the a is, what the x is, and what the y is. Okay, so my a, if you notice, is equal to 9. My x is 81, and my y is equal to 2. So then all we do is follow the formula, the a to the y power equals x. You see there's my a, which is 9, my y is 2, and my x is 81. Example number 2. Now we're going to go the other way. They're going to give it to you in exponential, and they want you to write it in logarithmic, as a logarithmic equation. So again, we have to know what the a, what the y, and what the x is. Right? Again, on the left, this is exponential, and on the right, this is logarithmic form. If you notice, my a is 5, my y is 3, and my x is 125. So it's equal to 3 equals to log a base 5 of 125, or log a base 5 of 125 equals 3. And okay, now this leads to graphing. In order to graph without a calculator, must convert logarithmic equation to an exponential equation. So I believe I'm going to show you two graphs, the exponential and also the logarithmic graph. But what are exponential functions, right? And again, this I covered last week. So this is an example of exponential function. You have f of x equals to 2 to the power of x. G of x equals to 750, 1.05 to the power of x. If you notice, the exponent always has a variable, which is x in this case. Okay. Now recall that a, this is a base to the power of m divided by n, is equal to f of x equals to a. For example, here the exponent, right, is a fraction, which is the same thing as x. Okay, this is my x, is my exponent. Now a is a base. The exponent is a variable, which is called a letter, which is a letter in math, which is called a variable, which is frequently x, but it can be any variable, any letter in the alphabet. Okay. Now this leads to graphing exponential equations or functions. Example number 3. They want you to graph the 2x. So like I said last week, it's always wise to use points, right? To use like -3, -2, -1, 0, 1, 2, and 3. This is a basic for all graphs. And then it depends how it moves. It depends what values you're going to put in for x. But this is called the parent function. So for the parent function, you always use these small numbers right here. This is the most common numbers used. Okay. So let's do a little table here. Right. This f of x is the same thing as y. Right. So let's start with -2, right? So when x is -2, right, we're going to plug in -2 for the x's equals to 2 to the -2 power, right? We use a negative exponent rule, equals to 1 over 2 to the second power, which is equal to 1/4. So when x is -2, y, or f of x, is 1/4. And we repeat the process until we plug in all the values for x here on the where x1 wants you to use -2 all the way to 3. So again, we repeat the process. We plug in the -1 for the x, And 2 to a negative first power is equal to 1 over 2 to the first power is equal to 1/2. So when x is negative 1, y is 1/2. Then we plug in 0. Anything to a 0 power is equal to 1. So 2 to the 0 power equals 1. So when x is 0, y is 1. Okay, now let's try 1. When x is 1, plug in 1 where the exponent is for the x's for the exponent. So 2 to the first power will give us 2. So when x is 1, y is 2. And then when x is 2, again, we repeat the process. We're going to plug in 2 for the x's as the exponent. So 2 to the second power is going to give us 4. So when x is 2, y is 4. And finally, we're going to plug in 3. So we evaluate at f of 3 equals 2 to the third power equals to 8. A common mistake that students make is that they multiply 2 times 3, which is wrong. Okay, so 2 to the third power is equal to 2 times 2 times 2, which is equal to 8. So when x is 3, y is 8. Okay, and there's my graph. You see, you notice this graph starts low, and as x gets bigger, the y begins to increase. That's why this is called an exponential function. If you notice, that's why the main points to use are from -3 to about 3. Because let's pretend that this is something like 5 to the third power. It's going to give us 125. So it's real hard to graph the graph if the base was a 5 and raised to the third power. It won't be able to fit it here. That's why the most common numbers to use are small numbers, small integers. Okay, so let me go to the next one. Now we're going to graph logarithmic functions. And again, this is what I did last week towards the end of my presentation. So I decided to do it again because these always give a hard time to students, these type of problems. So in order to graph without a calculator, I must convert logarithmic equation to an exponential equation. Right, so this is my logarithmic form. Y equals to log base ax is equal to a to the y equals x. So now let's graph y equals to log base 2x. So to convert it from logarithmic to exponential, it's going to be 2 to the y equals x. Now, but instead of plugging in values for x, we're going to plug them in for y. Okay. So again, this is a solution, right? Because y to the negative second power. F of x equals to 2 to the x, right? So here, the graph f of x equals 2x is the one in blue. Okay. And the log, the one in red, right? This is the one in red is a log graph. And these are my points here. Okay, let me go back real quick. This is a graph, right? Because when x is 1/4, right? X is 1/4, it'll be about right here. 1/4 is between, you cut the unit from 0 to 1, you cut it into 4 equal parts. So 1/4 will be about here, right? So go all the way down, you're at 2, a -2. Then when x is 1/2, right? So that means you cut this unit from 0 to 1, you cut it in half. So half will be about here, so that's -1. And then we got 1, 0. Then we got 2, 1. Then we got 4, 2. Then we have 8, 3. So the graph I use connect all the points, and the graph is something like it is right here in red. Okay, now these two functions are called inverse of each other. Okay, but that's another topic that we'll cover later on this semester. Okay, but for now, this was a quick review of what we learned last week. Okay, now this is the main topic for today: solving exponential and logarithmic functions. Okay, now to solve exponential equations without a calculator, you need to know previous topics such as perfect squares. So you got to know at least the perfect squares from 2 all the way to, from 1 all the way to 10. For example, 2 squared is equal to 4. So the square root of 4 equals 2 and vice versa. Okay, so this is what you got to know, and if you know more, it'll be better for you. Also, perfect cubes. For example, 8 is a perfect cube because 2 cubed is equal to 8. 27 is a perfect cube because 3 cubed is equal to 27, and so forth. So at least know all the way to 6. Okay? And now solve that fourth roots. At least know all the way to 5. And this is the exponential expression, right? A to the m, a is called the base, and m is the exponent. Also, you need to know the exponent power rules, right? When you raise a power to a power, you multiply the powers. And also, you need to know how to solve one variable equations, or maybe one variable equations, okay, such as like 2x plus 8 equals to 14. And also, when you do logs, you have to know how to factor, and stuff like that. So all these is what you need to know to solve exponential equations. Okay, let's do an example. So this is one of the rules or the definition, right? Or just a rule. This is called an exponential rule. If you have, it says, let a be a positive real number with a cannot equal to 1. Okay, now, if a to the power of u equals to a to the power of v, then the exponents must equal to each other. Number 5. Here we have 3, right? We have 3 and 3, right? So the bases are the same, right? That's what the rule says here. When you have a to the u equals to a to the v, right? The bases, which is a, have to be the same. So example number 5, the bases are the same, right? That's why we can apply the rule. So the rule states when you have the same bases, you let the exponents equal to each other. So in this case, x must equal to 5. Okay, very basic. This is very basic. Example number 5, but they get a little bit more challenging. For example number 6, 8 to the x power equals 2 to the fifth power. So if you notice, the 8 and the 2 are not the same, so they're not the same base. So then we have to simplify the 8 or the 2, right? In this case, it's going to be the 8. Because remember, 8 equals to 2 to the third power. Now, so we're going to substitute 2 to the third power for the 8. And we've done the exponent, equals 2 to the fifth, right? Now, here we're going to apply the power rule. When you have an exponent raised to an exponent, we multiply the powers. Okay? So it's going to be 2 to the 3x equals 2 to the fifth power. Now we got the same base. Now we can apply the rule. So the rule from above here, it says when you have the same base, we let the exponents equal. So 3x equals to 5. We divide both sides by 3. So x equals to 5 over 3. The good thing about solving exponential equations and also logarithmic equations, you can always check your answer. Okay, so let's check it. We have a to the x equals 2 to the fifth power, right? So we're going to plug in 5/3 for x because that was my solution. So if you plug into the calculator, it's going to give you, right? I mean, you can do it both ways, with or without. First, right? If you plug in a to the 5/3 power, it's going to give you 32. If you plug in 2 to the fifth power, we'll give you 32. Okay, now a lot of students have the old-fashioned calculators. So if when you put the power, right, the power, and if it gives you like a caret, like a little caret means like an upside down V, then you have to put parentheses here because that's a common mistake that students make. But when you plug into the calculator and if it gives you like a little box on top of the base to write the exponent, then all you do is plug it in just the way it is. Okay? But anyway, these are the same answer. So 5/3 is an answer. Now let's do it by using the exponential rule. When you have a to the mn, right? The n of the exponent is your index. The a is a radicand and the m is a power. So in this case, we're going to write a to the 5/3 power by using this property here, the fractional exponential rule. Right? Again, my a is my radicand, it goes into the radical. My 3 is the index, which is the denominator of the fraction of the exponent, and 5 is the power. So again, the cube root of 8, right, is going to be 2. 2 to the fifth power equals 32. That's how we apply this rule here. Now, example number 7. we have 9 to the x power equals to 27. So again, do we have the same base? No, not the same. So then we know that 27 is bigger than 9. So let's try doing, see if we can get a 27 when we have the power of 9 raised to a power. If we raise 9 to the second power, right, it's going to be too much. 9 squared is 81, which is not equal to 27. That means that we have to downgrade both bases for them to be equal. So in other words, right, we have to find a common base for 9 and 27, which is going to be 3, because 9 equals to 3 squared and 27 equals to 3 cubed. And that's why, guys, I mentioned earlier that before we start solving exponential equations, you have to know perfect squares, perfect cubes, all the way to the fourth power. Remember, I mentioned that about 2 slides ago. That's why it's crucial. Okay, now, so then I'm going to substitute 3 squared for the 9 and bring down the x as the exponent. And the same thing, I'm going to substitute 3 cubed for the 27. Now, here on the left side, I'm going to apply the exponent property rule, okay, or exponent power rule, which means when you have a power to a power, we multiply the powers. So 3 squared to the x power is equal to 3 to the 2 times x, and equals to 3 cubed, right? Now we got the same base, so now we can apply the rule. And the rule states, when you have the same bases, you let the exponents equal to each other. So we divide both sides by 2, I'm sorry. So x equals to 3 over 2. And again, you can always check your solution. So let's plug in 3 over 2 for the x's. And 9 to the third, to the 3 has power, it equals to 27. So again, this solution checks out. Okay. Okay, now you see that each one gets a little bit more challenging, right? But you apply the same concept. Okay, now we have 4 to the x minus 1 equals to 32. We do the same process as before, right? Not the same base. So let's see if 4 squared equals to 32. No, 4 squared equals to 16, right? And 16 does not reach 32, so let's try 4 cubed. 4 cubed equals 64, right? So that means that these you have to find the common base between 4 and 32. Okay, 4 equals to 2 squared. And 32 equals 2 to the 5th power. You see, so we found our common bases. So now we're going to substitute 2 squared where the 4 is, and we bring down the x minus 1, the exponent. And in similar fashion, we're going to substitute 2 to the 5th power for the 32. Now we apply the exponential, or the exponent power rule. Again, when you have a power to a power, we multiply the powers. So we're going to multiply the 2 times the x minus 1. Now, right now, we got the same base. Now we apply the rule. And I repeat, when you have the same bases, you let the exponents equal to each other. Now here we're going to distribute. 2 times x is 2x, and 2 times negative 1 is negative 2 equals to 5. We add 2 to both sides. So then we add 2 to both sides, it's going to give us 2x equals to 7. Then we divide by 2. So x equals to 7 over 2. And again, we can always check our work. So I'm going to plug in 7 over 2 for the x's. Right, so 4 is going to be 7 over 2 minus 1. 7 over 2 minus 1 is going to give us 5 over 2. So 4 to the power of 5 over 2 equals to 32, right? So now again, we put in the calculator, or we can apply the rule that it goes from the exponential, right, into radical, and it should give us 32. So 32 equals 32. So I know this is a solution. Now, let's solve, to solve logarithmic and exponential equations, you need to know previous properties such as, so also these properties, I believe you also, they were covered in one of the sections of this chapter. For example, if you have log of base A, you have x times y, right, is equal to log of base A x plus log of base A y. So in other words, these on the left, these are called condensed. The book might call it condensed, or the pre-cal book calls it condensed, or they call it in a single log, and this is called expanded. Single log or condensed, and this is called expanded form. So in other words, so when you're multiplying here, the x and the y, you separate them and you put log a base. So when you multiply, you add them with two different logs. Now, when you divide, right, when you divide, you're going to subtract. And the power rule means the exponent goes to the front, right? If you notice that the r went to the front, r was the exponent. This is called the product rule when you multiply. The quotient rule is when you divide, and this is called the power property, or, and it works the same way for the ln's, which, right? So when you multiply, you can add them, right? But you separate both ln's. This is called the natural log. In a similar fashion, when you divide, you subtract, and and the exponent goes to the front. Okay. So now, recall the example number 7, right? Remember where we had to find the same base? Well, it can be solved without getting the same base. It can be solved by taking the log or the ln. I like to take the ln instead, because when you get to the next chapter of finance, you'll be using the ln property. You don't use the log property. So that's why I like to take the ln on both sides. So for example, this was my answer, correct? Remember from the previous slide, the example number 7. Now, this is how you solve it, by using the property of the natural log. You're going to take the ln on both sides. You bring down the exponent by taking the ln on both sides, right? So you're going to take the ln of 9x and the ln of 27. Okay, now, this is very important here, guys. When I was doing, when I was in school doing the master's program, or I mean before that, I think, the instructor will always say, what you do to the left side, right? If you put the ln on the left, you also have to put it on the left, on the right side. Because if you put it on the right side, it doesn't make sense, of the 27. It has to be on the left side of both left side and right side. Okay? Now, use a power property, right? The exponent goes to the front, right? By property by this property here, right? The r, which is the exponent here on the property, it goes to the front. So when you take the ln, the exponent goes to the front. Okay? And then you rewrite it how it is, and then you divide both sides by ln of 9. Okay, now, right, so this x equals to ln over 27 over ln of 9, and then you use your calculator, and this is your solution. The answer is 1.5, or 3 over 2. Remember, guys, you see we got the same answer, 3 over 2, 3 over 2. Now, a common mistake, okay, this is a mistake that students make. They don't understand the log or the natural log. So then they just because they see, for example, they see like the ln of 7 over the ln of 3, they want to divide 27 divided by 3, which is not correct. The ln is actual value. The whole ln, for example, here, the ln of 27 is a number. The ln of 9 is also a number. They go together. You cannot separate them. So please do not make that mistake. Okay. Now here, we're going to be using another property here. It says that u and r are real numbers. With u being positive, then the ln of u to the r equals to r ln of u. In other words, the exponent, right, goes to the front. That's what I explained earlier in one of the properties, or the exponential, or the logarithmic rules, right? The exponent goes to the front. So now, here's we're going to apply the rule. Every time that you try to solve exponential equations, the instructors, they always say, try to find the same base. That should be your first step. And then if you don't find the same base, then you can apply this rule here, which is the ln rule. Okay, but if you don't want to go through finding the same base, right, you can just skip and use this property here. Okay, example, let me show you again how it works. So you're going to take the ln on both sides. Again, not same base and cannot get them with the same base. So you bring down the exponent by taking the ln on both sides. So I'm going to take the ln, right? Again, the ln, I'm going to insert the ln on the left side of the 5x. In a similar fashion, I'm going to take the ln on the left side of the 8. Now, right now, by using the property, the exponent goes to the front. Then we get to divide the ln of 5 on both sides. And now when you plug into the calculator, this is your result. You see I put like wiggly lines, which means approximate, because most of the times this would be like a I think it's called like a rational number. I mean like a irrational number. You see it never ends. It's going to be something like 1.290, right? And it goes on forever and ever. That's why these you have to round off to maybe 4 places, 5 places, or whatever the instructor wants you to round off to, or the book and the instructions, they want you to round off to a certain amount of decimal places. I believe most of the times the number of decimal places that they want is either 4 or 5 on your Mind Math Lab. Okay, so now we can check our answer, right? Since we rounded off, the answer is not going to be exact. It might be something like 7.9999 something, or maybe 8.0001, but it's going to be very, very close to 8. Okay, so again, we're going to plug in the 1.2920 for the x, right? Plug into the calculator. You see, this is what we get, 7.9996. And it's a little bit short. Why? Because we rounded off, right? So that's why this runs off to 8. So this is the correct answer. Okay, now, here's another property. Let U, V, and A be positive real numbers, with A cannot equal to 1. So if log of base AU equals to log of base AV, then U equals to V. It's similar to the exponential rule, right? When you have the same bases, you let the exponents equal to each other. Here, guys, when you have the same logs with the same base, then you let whatever the value for U is and for V is equal to each other. Okay? Example number 10. You have a log of x equals to log of parentheses 3x minus 6. If you notice, there's no base, right? There's no base there, nor there. So that means it's base 10. Because base 10, they don't really put the 10 there. We know it's base 10, and also we should know that it's base 10. Same thing when you write x, right? Isn't x equal to the same thing as 1x? But we don't put 1x. We know just by x by itself, we know the coefficient is 1. Same thing here with the logarithms. If there's no base, the base is going to be 10. And I believe I went over that in last week's PowerPoint. So again, right, we have the same log with the same base, right? Single log. Again, you see they both have to be single logs on both sides. So single log with same base on both sides, you apply the rule. So the rule, it means when you have the same log with the same base, and they're both single log, we let the U equal, let x equals to 3x minus 2. Now all you do is subtract 3x from both sides, right? So minus 3x minus 3x. So it's going to give us negative 2x equals to negative 6. Then we divide both sides by negative 2, and it gives us x equals to positive 3. And again, you can always check your work. Okay? Check solutions. Okay, now. Hey guys, one thing that you have to know, right, that is crucial for logarithms. You cannot have for example, leg of x, right? The x has to be more than 0. It cannot be 0 nor negative. I always tell my students, okay, guys, the logs, right? The domain has to be more than 0. Okay, now, so then I tell my students, plug in the log of negative 3. See what you guys get. And the geometry says it says like okay. Now that I have, let me see exactly what it says, okay? Because I have a calculator here. Every calculator says something different, but I have a Casio. I'm going to put the log of negative 3, right? It gives me math error. And okay, so that means that the logs cannot be negative. Now, if I plug in the log of 0, it's going to give me the same thing, right? It gives me math error, which means that the logs cannot be negative nor zero. Now, I have my calculator here with me. I'm going to plug in log of 0.00001, right? Which is almost the same thing as, well, it's almost equal to zero, right? But it's a little bit more than zero. So 0.0001 is going to give me -4. So in other words, the logs has to be more than zero. So every time that you get a solution that's negative, that answer cannot be it. Okay? So again, let's check our answers. So I'm going to plug in when x equals 3, right? I put it here in green that I'm going to plug in the 3 for every x. So I'm going to plug it in there where the x is, the 3. Here we have 3, right? So the x is 3. So here we have 3 times 3. So 3 times 3 is 9. 9 minus 6 is equal to 3. So log of base 10 of 3 equals to log of base 10 of 3. So the solution, this is a solution. Let me go back. You see, this was a solution. Hey guys, I'm having trouble with my mouse. I need to click it like real slow, or else it'll double click. Okay, maybe I need to change mouses, or maybe get a new battery. But anyway, that was a solution. Now let me try. Let's do another one. Okay, now here you have log of base 10 again of x plus 3 equals to log of x minus 2 plus log of x plus 3. And again, right, you don't see a base there, so we know it's base 10. So I know all the bases are the same. So to apply the rule, the single log must be on both sides to use the product property on the right side, okay? So this is what it means here. You see, guys, the rule here above, there have to be a single log on the left and a single log on the right, then also with the same basis. So then the u must equal to v, right? But here, guys, on the left side, it's a single log. On the right side, it's not. So we have to use some of the logarithmic properties that I mentioned about 2 slides ago. So in this case, right, so we're going to use the product property on the right. The product property means when you have addition, right, this is called expanded form. You want to condense it to a single log. So when you have addition, right, between 2 logs with the same base, then this becomes the product property, right? So this is called expanded, and this is a single log or condensed form. You see, again, when you apply the product property, right, you separate them and you put a plus in between with a log of each term here. So again, this is expanded form, this is condensed form. Now you have single log on both sides. Now we can apply the rule. Okay, so the rule states, right, when you have the same base, log with the same base on both sides, then the x plus 3 must equal to the x minus 2 times x plus 3. So here we have to multiply, right? We have to multiply the binomials, or it's called FOIL. Again, the FOIL method is like this. You're going to multiply the first times the first, right? So x times x equals to x squared. The first times the outer, which is or the O stands for outer times outer, right? So x times positive 3 will give us positive 3x. The I stands for inner. You're going to multiply inner times inner, so negative 2 times x gives us a negative 2x. And the L stands for last. We're going to multiply last times last, so negative 2 times positive 3 will give us a negative 6. Now you're going to combine like terms. So 3x minus 2x will give us an x. Now I need to set the equation equal to 0. So since we have x squared here on the right, I'm going to send the x and the 3 to the right side by doing the opposite, right? So the opposite of positive x is negative x. The opposite of positive 3 is negative 3, but I need to do it to both sides. So on the left side, it's going to give me 0. On the right side, since we don't have no like term for the x squared, we just bring it down. We have x minus x, right, will give us a 0. And negative 6 minus 3 will give us a negative 9. Now we need to factor. And hey guys, let me say something about factoring just real quick. Hey guys, factoring is crucial, especially if you're going to be taking another math course. There's some students right now in some of my classes that are taking upper level classes, not just the next one, but upper level classes, and they don't know how to factor, or they're having a hard time factoring. I need to do something because if they don't know how to factor, it's going to be hard for them to keep going in mathematics or to pass my class. So again, guys, factor is very, very important, guys. So here, I believe I went over this workshop on factoring about I think in week 3. You can look back at that PowerPoint or that presentation that I did, and it covers every form of factoring. So x squared minus 9 is equal to x minus 3 and x plus 3. That's how you factor it. Then we're going to set the binomials, right? These are called binomials. We're going to set them equal to 0. But I believe it's called the zero property rule. So x minus 3 equals 0 or x plus 3 equals 0. Now all I do is solve for x. Right? So if we add 3 to both sides, right, it's going to give us x equals 3. On the right side, if we subtract 3 from both sides, so negative 3 and negative 3 is going to give us x equals to negative 3. So these are my two solutions. But guess what, guys? We have to check them. So check both solutions. A lot of my students will tell me, Mr. Isasi, do we have to check him? Yeah, you do. You have to check the answers because at times they're not. I mean, it's not a solution like I'm going to demonstrate right now with a negative 3. Right. So when x equals negative 3, right? I'm going to plug in negative 3 for every x. See, negative 3, negative 3, negative 3. Negative 3 plus 3, right? That's undefined because remember I mentioned that I plug into my calculator. The logs cannot be 0 or no negative. They have to be more than 3. So if one of them is not defined, then the solution is not a solution. So in this case, the negative 3 is not a solution. Okay. Now, when x equals to 3, again, right, when x equals 3, I'm going to plug in 3 for every x. So I'm going to plug the 3 there for the x on the left side, and on the other 2 logs on the right side, 3 and 3, right? So here we have a log of 3 plus 3 will give us 6. Log of 3 minus 2 will give us 1, and log of 3 plus 3 will give us 6. So also, if you have a calculator handy, plug in log of 1. It should give us a 0. Or it is 0. It shouldn't give us, it is 0. Okay, so log of 1 equals 0. So then, right, so then we simplify here. So log of 6 equals to log of 6. So I know this is the answer. So 3 is this a solution. Okay. Now, same rule, okay, but now this is a different example. I did one where they both had the same logs, right? I mean on both sides, single logs. I did one with a product rule. Now this with a minus, we're going to use another property, right? Which is a quotient rule or the quotient property. Again, to apply the rule, single log must be on both sides. On the left side, we're okay. On the right side, we're not okay because we have log of x plus 3 minus log of x minus 1, and both bases are 10. Same thing as the left side. So here we apply the quotient rule. The quotient rule was when you're subtracting, right, then this becomes you put them in a single log. The first term here on the log goes as a numerator, and the second term on the log, the minus 1, goes on the bottom as a denominator. Now we have the single log on both sides. Now we can apply the rule. Again, when you have, like the rule states above, when you have the same logs with the same base, right? This is log of base 10, log of base 10. So we let the x equals to the x plus 3 over x minus 1. Now this can be solved in different ways, right? You can multiply x minus 1 to both sides, or you can cross multiply. For example, x can be written as x over 1. So I'm going to multiply the x times x minus 1 and the 1 times x plus 3. Okay. Or like I said, or you can multiply both sides by x minus 1, right? So x minus 1 on the right side, the x minus 1 will cancel. So we're left with x plus 3. And the x minus 1 times the left side, we'll just have x times x minus 1. Now here, right, on the left side, we have to distribute. Like x times x will give us x squared, and x times negative 1 will give us negative x. Now, right, since the x squared is on the left, we need to set it equal to 0 on the right side. So we're going to subtract negative x plus 3, negative x minus 3 to both sides. Right, this is going to give us a 0 on the right side. Okay, now x squared minus 2x minus 3, now we got a factor. Okay, we got a factor. So x squared minus 2x minus 3 is equivalent to x minus 3 and x plus 1. We set the binomial is equal to 0. So x minus 3 equals 0, or x plus 1 equals 0. So we know that the solutions are, so for x equals to positive 3 and x equals to negative 1. And like last time, we can check the solutions. So let's check them on the next slide. So this was my log equation. So I'm going to plug in first negative 1, right? So when we plug in negative 1 on the left side, right away, we know this is not defined. So I know this is not a solution. So let's check the positive 3. Right, so when x is 3, right, we plug in 3 for every x. So now it gives us log of 3 equals to log of 6 minus log of 2. If you put that in the calculator, right, it's going to give us, this will be the answer. But this, we can do it another way, by hand. Remember, guys, on the right side, right, we put it into a single log, right? If it's minus, then it means by applying the quotient rule, it's going to be 6 divided by 2, right? Again, we condense it into a single log, the log of 6 minus log of 2, and then it's going to give us log of 6 divided by 2. So it's going to give us log of 3 equals to log of 3, which is a solution. So 3 is my solution, and negative 1 is not. Okay, now we have another property here. If you have a to the power of log of a, u equals to u. Okay, how does this one work? This is how it works. Okay, guys, if you notice, the log of 3 of 6x minus 2 is the same thing as the log of a of u. Okay? Okay, now if we notice, we have to, we want to get rid of the log of base 3. We want to cancel it. How do we do that? Is we take what the base is here, we're going to put like a big 3 here, a big 3 there, and a big 3 on this side. So the 3 is like your base now. Okay, so if that was a 4, then it'll be 4 here and 4 here. So 4 becomes a base. Now, by applying the rule here on top, if you have the base, right, and you have the log with the same base, you see that's equal to whatever's in here. This is like my u, the 6x minus 2 is like my u. So that means that these, right, I've said that we can apply the rule. So then that means that these, right, cancel is equal to 1. So we just bring down the 6x minus 2, and 3 squared is equal to 9. Now all we do is just solve for x. We add 2 to both sides. So 6x equals to 11. Now we divide both sides by 6. So x equals to 11 over 6. And like before, we can always check our work. Okay. So here we're going to check it. Okay, we have log of base 3, parenthesis 6x minus 2, close parenthesis, equals to 2. So I'm going to plug in 11 over 6, right, where the x is. So this, right, so 6 divided by 6 here, guys, right, because we're multiplying, this will give us 66 over 6, or we can cancel the 6's, right? 6 divided by 6 is 1. So we're left out with 11 minus 2, which is log of 9 equals 2. Now, if you put this in the calculator, right, but you put in the calculator, you have to use the change of base. Or, remember the rules, I mean, guys, when you have like log of 3 of 9, how do we find the answer? This is how you read it. 3 raised to what power gives me 9? And I believe I did that on the last part, on the last presentation that I did last week. Again, here's how you read it. I mean, without the calculator. The base raised to what power gives me 9? So the answer is 2, because 3 squared gives us 9. So again, the 2 is my solution. I mean, the 11 over 6 is my solution. Hey guys, I'm done with this presentation. I hope that that's going to be helpful. Let me end the presentation, and that way I can go back to Blackboard here. Okay. I finished like it's 11:48. Does anybody have any questions?
Thank you, Mr. Azasi.
Oh, you're welcome, Patricia.
Antonio, Carla, do y'all have any questions for Mr. Azasi?
No?
Oh, okay. No
Thank you,
problem.
Antonio. Thank you.
All right. Well, if there's no further questions, I'll go ahead and wrap us up. We'd like to invite you to next week's Happy Math Hour at 11 a.m. with the same link. For Math 1314, we'll be going over finding zeros of polynomial functions. And for Math 1324, we'll be going over simple and compound interest annuities. And that's a big section of Math 1324, so we'll hope you come back and see us. As well as next week at 1 p.m. at the link, we'll be having resources and services available at EPCC and the El Paso community, presented by the EPCC Mental Health Committee. So we would like to thank you for joining us today. Thank you to Mr. Azasi for presenting today, and I hope you all have a wonderful weekend.
Bye-bye, guys. Thank you, Patricia.